Are you going to think it's moving?
Welcome to the teleconference service. Please enter your access code, followed by the pound sign.
Oh my God.
The host has not yet arrived. Please stand by. At the tone, please speak your name.
Shreyasee? Hello?
Hi, morning, good afternoon, Shreyasee.
Good morning, Ravi. How are you?
I'm doing good. How are you?
I'm good. You can listen to me loud and clear, right?
Yeah, you're fine.
Okay.
So can I see your, can you share your desktop here? I haven't done that on Skype before. So.
Yeah. So, let me try sharing the screen, and if that's, because if I point the camera towards the projector, there's some disturbance. So let me just try doing share screen. Ravi, you have to accept my call.
Okay, where is it? Oh, it's coming on mobile phone. Okay. So I don't know how do I. So is it something like? Okay, let me call you then.
Okay.
Probably that will work.
Sure.
You want a video call or a regular call?
I think video to share the screen. I just share the screen now.
Okay, just wait, let me mute myself. Huh?
And then share screen.
Oh, okay, you're putting it on video. I thought there was a way to share the screen itself.
I think this is okay, right?
Yeah, this is fine, yeah. This one you have your laptop pointed at the thing, right? Or you're sharing the screen here?
I'm sharing the screen which has the slides, but you'll see it in the presenter mode. I don't think you'll see the full thing.
Oh, okay, yeah, sure.
But this is okay. Like this.
I don't know if he sees this or if he sees that. I don't know what he's seeing.
Oh, what are you exactly seeing? Are you seeing the?
Yeah. I mean, I see your your slides. I mean, that's in the forefront, okay. And I see a small thing, a small sized thing of the video. I mean,
okay.
But this takes the screen, yeah.
Okay. Yeah, we are just waiting for a couple of minutes for everyone to.
Oh, sure.
Professor Mukherjee.
He said we'll be a few minutes late.
Yeah.
These spongy things are very good.
Thank you.
Since you made them.
Like they look like they're going to be a dessert thing, and then they're not. Which is very, no, I really like them.
Thank you.
So is it dokla? Shaped like a idli?
Yeah, because I only have an idli maker to make it.
So it's the Western Indian snack made with the South Indian
Demanding a picture.
A shape.
shape. Yeah.
Just have to stand next to you.
You had those rice cake things which are like this
I don't remember them. But what shape would this normally be?
Cubes.
Cubes.
Interesting. So, Ravi, you're there? Hello?
Yes, good afternoon, Professor. Yeah, I'm here.
Yeah, so we'll just, we have to wait a couple of minutes for Narayan to show up. He has a meeting on campus.
No problem.
So did your parents want you to be a medical doctor, and this is the way you get even with them?
Yes.
It was meant in that.
Not sure whether that works out. Okay.
Because I don't think there will be
Right, so because the thing is they have some children, sometimes they say, okay, we have 5 at home, and sometimes they say we'll have 4 at the back door.
Okay, so I think we should get started, and Narayan said he'll come in. So Ravi will get started now, and let me just introduce again. I don't need to introduce Shreyasee is our senior student in networking, and she's graduating with a PhD and going to join work at Google fairly soon. So she was actually one of the first to join the Mobility First project and has worked on the core networking technology aspects. So her thesis is mostly about that. Okay, so please start. And if you can keep it within about 50 minutes or maximum 1 hour.
Okay, sure. You can go there. Good afternoon, everybody. Thanks for coming to my defense. I apologize that I caught a cold recently and I might cough a bit or sneeze a bit. Please excuse that. I hope I'm audible. Ravi, you can hear me from this distance, right?
Yeah,
Okay.
you're fine. Absolutely fine. Yeah.
Okay. So, welcome. My thesis is titled Network Protocols for the Mobility-Centric Future Internet. This doesn't work. My laptop froze.
You have a pointer, so try exiting. And
I think it's because I'm sharing the screen on Skype. So, something's happening in the background. Still sharing. That's this one here.
If this is a problem, Shreyasee, you can just mail me a slide and just tell me what slide number you are in, and I can follow to that.
Let's see. Whoops.
Oh, yeah, it's advancing now.
No, that's I'm clicking manually on the. Okay, I'll just do that.
do it manually.
Yeah. Okay. So yeah, my thesis is titled Network Protocols for the Mobility-Centric Future Internet. To introduce the topic, this figure just shows how the internet has evolved over the years. So the internet started with mostly static n-hosts and a few big computers and servers on both ends and a homogeneous network. And over the years, it has evolved to over 6 billion devices, and and the devices are all heterogeneous. So there can be smartphones, there can be smart vehicles, wireless sensors, and so on. Not only that, the type of networks connecting through the internet has changed as well. So you have vehicular networks, you have wireless access networks, you have content delivery networks, and so on. However, in comparison, if you look at how the network protocols managing the internet has evolved, you see that the protocols haven't changed that much. For example, TCP/IP, which was introduced in the late 70s, it's still pretty much in use now. BGP, which is the de facto interdomain routing protocol, was introduced in the late 90s, and it's still the only routing protocol that's being used for routing packets globally. There have been some modifications. For example, IPv6 was proposed, which was an extension of IPv4. Mobile IP was proposed. These were proposed in order to counter the increasing number of devices as well as mobility. However, even up to this day, they are not very much in use because it's kind of difficult to change the internet and overhaul it as such. So the organization of my thesis is I start with the network requirements, looking at what do we need for the future internet, and then we, as part of the Mobility First group, propose named objects as a potential solution to address some of the mobility related issues. So I describe what are named objects, followed by a brief overview of Mobility First, and then we dive into 3 of the protocols which I've worked on based on the concept of named objects, namely edge-aware interdomain routing, named object multicast, and our latest work on low latency mobiles core network for cellular communication. My thesis also does some comparison of Mobility First with other alternative name-based architectures as well, namely host identity protocol and location identifier separation protocols and so on. So we begin with the network requirements. This slide just highlights some of the main requirements that we need to take care of moving forward. To start with, there is a lot of mobility, and it is not just host mobility, it can be network mobility, it can be content mobility, everything is becoming more and more mobile. And we think one of the best ways to address mobility is to separate names or which are identifiers for any network connected objects from their locators, which determines where the object is located. And this is one of the drawbacks of IP, which is used both as a name as well as an address, and as such when a device moves, it needs to get a new name, and that causes a lot of issues with routing and forwarding. Next, there's varying link quality and disconnection that needs to be addressed, because there are wireless links that typically go down when you're moving and you're disassociating and associating with new networks. As well as there are newer forms of networks such as vehicular networks, which are dynamically formed and they opportunistically connect to the main internet whenever there's a wireless link available. So we do need to address that. The next is accessing multiple networks. For example, when you have a mobile phone with Wi-Fi and LTE and you want to connect simultaneously to both the networks, and this is becoming more and more common. And a way to address that is again to have a single name binding to multiple addresses, and then having the routing plane intelligent enough so that it can efficiently route across multiple paths to a single end device. Ad hoc networks are also popular. Again, going back to the vehicular scenario, you have groups of cars forming an ad hoc network and then opportunistically connecting on the highway. Not only that, so that's the opportunistic network formation part, but not only that, it also means that if networks are being formed opportunistically, there should be some mechanism to have the routing and the basic network services to bootstrap within that network. Content and context addressability is also becoming important. As such, people don't care about where the server is located. All they want is a piece of content. So it would be cool to have a network where you can just ask for a content instead of going to an IP address and asking for a specific content. And finally, as with any networks, a future internet architecture should have strong authentication and security primitives. So there should be mechanisms by which end devices can be authenticated, and the key management infrastructure should be efficient as well. What is our named object solution? This is a figure produced by my colleague Francesco, and this provides an overview of what a named object is. At the core, it is identifying what the end devices are, that is the what part of the entire solution, and then where identifies where this device is currently located. And then there should be a mapping infrastructure which would map the what to the where. At the same time, for named objects, what we also have is a hint which can be stored in this mapping infrastructure, which indicates how should packets be routed to this device, as I'll explain later. Given this separation of what from where, now you can imagine different kinds of services that can be enabled by this named object. For example, you can have the standard and two devices communicating with each other, but you can also have multi-homing as shown in the bottom right, where a single end device has two interfaces. So the mapping service now stores a single name to multiple addresses. You can have content where content is assigned a name on the top right. You can also have something like a virtual link or virtual networks being defined based on these names. And again, this can be stored in the mapping infrastructure, so that when packets are assigned these names, they can be looked up in the mapping infrastructure to figure out how to route them. This slide gives an overview of mobility first, which is one potential named object solution. There are other alternative architectures as well, but my thesis has focused only on mobility first. So what mobility first does is, for mobility first, the names are globally unique identifiers or GUIDs. They are based on public keys. They are secure 160-bit IDs. The locators are network addresses, which are also flat in mobility first context, so we do not use IP. The name resolution service is a distributed service. This is the mapping service I've been talking about, which stores the mapping between the name to where the name is currently located in the internet. The packet carries both the name and the address, and this helps in case of mobility. So for example, if the device moves, in this case if the phone moves and connects to a different network, en route packets can be looked up on the GNRS again, and then can be rerouted to the correct location once the correct locator has been put in the packet. The packets also carry a service identifier, which indicates the how part of the named object. So it gives an indication on how this packet can be routed. Some examples of SID can be, if a device is connected to two interfaces, the SID can indicate send data only across the best interface. So the routers can take that decision and on the fly choose which interface is better and route packets towards that interface. The mapping service or the global name resolution service, there are multiple implementations of it in Mobility First. The one which I have primarily used for all my evaluations and experiments is based on distributed hash tables. It's logically centralized but physically distributed, and for each mapping there are multiple locations where this mapping is stored for resiliency and reliability. So given the named object solution and mobility first, my research roadmap has been to look at the requirements which I described earlier and propose protocol solutions to address those requirements. In today's talk, I'll be talking about three of them: edge-aware interdomain routing, named object multicast, and some protocol advancements to cellular core network. And the goal again has been to look at the requirements and to see how best they can be addressed. I have also worked on a few other projects, mostly throughout my PhD and master's research. I've worked a lot on mobility and multi-homing. I've worked on comparing different types of named object architectural solutions and how best they address the requirements. I've also worked alongside Parishad in some of the standardization efforts for named object solutions, but due to constraints of time, I won't be talking about them today. Okay. So moving on to the first big part of the talk, which is edge-aware interdomain routing. So as you all might know, interdomain routing is the routing by which different autonomous systems in the internet talk to each other. The de facto routing protocol that is in use today is the Border Gateway Protocol, or BGP, and that has several limitations. On the right part of the slide, there are two use cases which highlight things that cannot be supported by BGP right now. For example, if you have, again, a device which is multi-home, so it has multiple interfaces connecting to the internet, and in most of the cases, these interfaces belong to different networks. So the routing protocol should be able to support some link quality awareness by which it can forward packets across these multiple links which belong to different networks, and this is not supported today. On the bottom right, you have another use case where you have an ad hoc vehicular network, and you can imagine this network as it moves across a highway. It peers to various other autonomous systems as it moves. So fast network formation and peering is currently not supported. The main drawback of BGP is its routing updates are pretty slow. So even if peering is supported, the update take too long to propagate throughout the internet. So by the time that information reaches some other network which needs that information, the ad hoc network has already moved on and changed its connectivity again. So yeah, like I mentioned, these are some of the basic properties of the future internet, and current BGP has poor support for all of these. So what are we proposing? In EIR, the main idea is, so in BGP what happens is every autonomous system just propagates a single best route to itself, to all other IP addresses that it can route to essentially. But in EIR, what we are saying is, we give the flexibility to each autonomous system so that they can advertise some of their internal topologies. And it's up to them how much or how little they want to expose. So what they do is, based on their internal topology, they create a graph of aggregated nodes and virtual links, and along with that, some properties of these virtual links, which can be average bandwidth, latency, and so on. And they propagate this graph, they put this graph in a network state packet, and they send this packet out to the rest of the internet. So what happens is, once every network receives one of these packets from all the other networks, you get a global view of the internet in terms of this aggregated nodes and virtual links. So you have multipath, you have link quality awareness, and then you can build multiple routing tables based on each of these V-link parameters. Again, it's flexible, so each network can choose whatever aggregation policies they have, how much or how little they want to expose. But the goal is, once you have that network state update, you receive it, you send it out to all the other networks, so everyone has a global view. As you can imagine, one of the problems with sending out your update to everyone else in the network is control overhead. You're essentially flooding a network state packet from every autonomous system to every other autonomous systems in the world, and this doesn't scale if you do simple flooding. To address this, what we proposed is something called a telescopic flooding of state. What this means is, anytime a border router receives an update, instead of immediately sending it out, it waits for some period of time, before which, within that time, if it receives a new update, it just discards the old update and keeps the new update, and when the timer expires, it sends the new update out. What this does is, it reduces the control overhead, because you're not sending out every packet. You're holding a packet for some period of time and sending only the fresher update out. The drawback of this is, not everyone will have the up-to-date information, because updates are being propagated slower, further and further away. But nearby ASs would still have a better view of the network, because they would be receiving every update. And the intuition here is that you don't really need to have the up-to-date information at all the other ASs, as long as you have some path reachability information so that you can send the packet out. The packet anyway will get rerouted if the path has changed by the time it moves closer to the receiver. We wanted to see what sort of telescopic functions can we use, so that gives us a balance between how stale the information is versus how much control overhead does the network incur. To do this, we started with, which is not there on this slide, but we started with some Network Simulator 3 NS3 simulations, where we had a 200 node jellyfish topology that mimics the internet topology, and then we tried a different bunch of telescopic functions to see what best has a reasonable overhead versus reasonable settling time. By settling time, which is also there on this plot, we mean the maximum time it takes for one packet to be available at all the other networks in the system. So it's the worst case time that an update reaches all the other networks. So we did some NS3 simulations, and based on that we figured the telescopic flooding function, which is shown on the top right, was the one which gave us the best results. This is a constant exponential constant telescopic function. So for a few hops you hold it for a constant time, then from then to a few next hops you hold it for exponential time, and then again you hold it for a constant time. But we still want to ensure that for an internet scale topology, what sort of exact numbers, what should be the exact equation by which should guide this telescopic flooding. To find the parameters of this telescopic function, then we moved on to an internet scale topology. We obviously couldn't run it on NS3 because of the scale, but we wrote a custom simulator in Python where we fed in the complete internet topology, which is available in Qaeda. This has around 47,000 ASs. It was, I think, around 2016. I'm not really sure the year, but there might be more recent ones now. So at that time it had 47,000 ASs and 200,000 links and so on. And we tried different values of the telescopic function to see what's the global control overhead and what's the settling time for that particular function.
Different values of the telescoping function means like different like that function but with different parameters for
Right.
A and alpha and beta.
Yeah. And so the result that we obtained is shown on the bottom left, where we see that for certain values of A, alpha, beta, there is a trough in this plot, right? So for certain values of A, alpha, beta, there is the network overhead is low, as well as the settling time is within reasonable, around 500 seconds, I guess, that's on, or something like that. So the goal was, now that we found these parameters, even if we run small scale experiments, which we later did on orbit, we chose values from these telescopic functions to use because these are more realistic numbers, as this was run on the complete internet topology.
What makes them more realistic than, say, 1/10? Like, suppose you made them all, you scaled them by a factor of 10 and you settled in 50 seconds, not 500. Isn't that better?
Yes, but the network overhead would also be higher in that case. So you'll be flooding more control packets over the internet, which would be okay if the links can support it, but in general these are not data packets, this is just control packets to set up the routing. So this side it's in Gbps network overhead.
So it's kind of the y-axis is the overhead,
Right.
and it's in gigabits per second.
Yes.
But that's over like sum totaled over 200,000 links.
Yes. So that's the other plot which I have on the right, which is per link what is the overhead.
Where is one of those the per link?
Yeah, this is the average link load. And this is the worst case and this is the average case. So again, for different, this is only for the values which were the ones which we found had lower overhead versus settling time. So for those values we figured out what's the average and worst case link load, and that's around, the worst case is around 250 Mbps, but the average is around 15, a little less than 15 Mbps per link. But again, if you have...
So is that pretty terrible or pretty good? Like,
that's okay, because these are interdomain links, so they would have upwards from 10 gigabits per second, I imagine more. These are between networks. So if you have an average 15 Mbps of routing overhead, I think that's reasonable.
maybe it's too good. You know, I was just saying, it seems like, so if they're 10 gigabit links, you could afford 10 times.
Yeah, I mean, you can always...
megabits per second or something.
You can always move towards the left of this network overhead plot and then trade off with lower settling time. And then you'll have more network overhead. Right?
Yeah, but you know.
But we also have some results which show that you don't really need the entire routing to converge. Even if you have transiency in the network itself should be able to reroute the packets to the correct location. So you don't really need to achieve that settling time, like wait for 200 seconds before you can actually send out a packet correctly.
Hi Shreyasee, I mean, is it okay to ask question or do you want to wait till the end?
No, sure, go ahead. You can ask questions.
No, so my question was like, I wasn't clear, like how is any domain using this abstract topologies? I mean, you typically, this kind of state information you could use either for signaling a path or you basically do some kind of source routing. So, how is any domain using it?
So,
if you want to cross multiple domains.
Yeah, so this is goes out in a network state packet. It's a routing packet. And that is being propagated to all the other networks. So for source routing, that happens with the data packet, right? You actually establish the entire path. So here the network state updates goes out, and then everyone runs. I forgot to mention actually, everyone runs a Dijkstra sort of routing algorithm to find the shortest path based on this graph. So your forwarding table would be based on all these network state updates. You'd run some Dijkstra.
Okay, so I mean, so the one way is that everybody, I mean, if you're basically crossing domain boundaries, right? I mean, you could say that, okay, I want to find, so you basically say, so either you have treat this as an entire, global topology and every router has this state. The other thing is that you divide that into intra-domain state and put some state in the packet so that the packet can go across the path, go on the path that the router, the source determines. So,
so this only
what is the routing? How are you forwarding here? What is the forwarding state in the router?
The global forwarding state is there at all the border routers. For the internal routers, you have your own intra-domain topology, and on top of that, we have a label-based path setup, which are not there in the slides, but it's there on the thesis, how we set that up. So intra-domain routers don't carry the global state. They have some simple label-based path forwarding from one border router to the other, whereas the border routers would have the complete state of all the A nodes in the entire internet. Does that answer?
Yeah, sure.
Yeah, so my next slide is actually on the state maintained at each of the routers and what's the scale, how much does each border router need to maintain. So for this simulation, we actually needed the internal topology of the autonomous systems because we needed some sort of aggregation factor by which each AS would abstract out their internal topology. This data set is a bit older because the more up-to-date data set didn't have any internal topology available. This is again from Qaeda, and this one had 11,340 ASs, but it also had their internal topology in terms of point of presence or POPs. Like I mentioned earlier, that in EIR we give the flexibility to each autonomous system as to how they want to aggregate their information. But for the sake of this evaluation, what we did was everyone aggregates uniformly. So, for example, if the aggregation fraction is 1, which means every autonomous system just advertises a single A node. Whereas if the aggregation factor is 1 by AS size, which means every POP within that autonomous system is being advertised as a separate A node. So, if every POP is being advertised as a separate A node, the amount of states being stored or the number of A nodes in the topology is of course much higher, whereas for one it's just the number of ASs in the system, which is 11,340. And what we wanted to do is compare this with what exists in BGP, what's the table sizes in BGP. So we looked into the CIDR report, which is a publicly available report about what's the table size for BGP for that specific year and month. And what we observed is that for moderate levels of aggregation, the EIR table sizes are actually comparable to BGP table sizes. And this is important because in BGP what happens is the table sizes are not determined by the number of ASs in the system, but it's actually the number of addressable IP prefixes. And it's very hard to aggregate IP prefixes nowadays because IP addresses are not assigned in a standard manner. So if you can't aggregate a prefix, you need to have a forwarding table entry for that prefix. Realistically, what we are expecting is autonomous systems would aggregate quite aggressively. It wouldn't actually give out all its pop level information. So in a realistic sense, I'm guessing that the routing table would be, for EIR, would be closer towards the right hand of the curve, so which is much lower than current routing table sizes. We also, along with the simulation, we also prototyped EIR, and we ran some experiments on orbit. The top right figure shows the click modules that we added to the existing mobility first click prototype to enable EIR. And what we did with that is we wanted to run some network mobility emulation cases on orbit. So we looked at San Francisco and we parsed some bus traces from San Francisco, and the use case is a bus is acting like an A node, and as it's moving, its connectivity to the internet is changing. So there's a routing update going on which says that now my neighbor has changed, right? And what we wanted to evaluate is, because this is a highly mobile, this is a reasonably mobile scenario, the bus is changing its connectivity quite frequently. What we wanted to see is, given our telescopic update, if there's a source somewhere far, far away trying to send data to this bus, how much of the data packets are getting lost because the routing update is stale. So again, we did telescopic, we plotted the data undergoing temporary storage. Data is actually not lost in Mobility First because Mobility First has a hop-by-hop reliability. So even if you can't deliver to the next hop, the routers would temporarily store the data and reroute it. So that's why the plot on the y-axis, it says temporary storage and not lost. And we looked at different bus routes. The bar chart here shows for 8 different routes what happens, how much percentage of the data is being stored for different telescopic functions. And we observed that on the worst case, it's around 3%. And this is because even though the bus is changing its connectivity quite frequently, because of the nature of the telescopic function, the source really doesn't need to know the exact changes in the routing topology. As the packet moves closer and closer to the destination, the update is fresher and the packet automatically gets rerouted to the correct location. So in summary, I also have a lot more results in the thesis, so if you're interested, please feel free to take a look at it. We proposed an edge-aware interdomain routing. We did some NS3 simulations. We also did Python-based simulations on complete internet topologies, and we deployed a prototype. We made a prototype and tested some small-scale experiments on orbit.
So one question, Shreyasee. So you mentioned something called label-based routing for forwarding the packets
Right.
within domains. So I mean, so the basic thing is that you have your destination UID, you get your basic final network address, right? And then the border nodes have this abstracted topology for the global interdomain topology. So is it that when you say label-based, are you tunneling the packet within the domain? Or?
Yes, we are. So from the border router, it sets up a path to the ingress border router sets up a path to the egress border router, and then it's tunneled through the intradomain. And then again, the label is taken out and the packet is forwarded to the next network.
Oh, okay. Hmm.
And
No, because when you tunnel it, I was thinking because when you tunnel it, right, I mean, you also have, the advantage you do with the store and forward is when you're actually doing name-based forwarding. So when you're tunneling it, probably in the final thing, you still do name-based forwarding, you don't do tunneling, I guess.
yeah,
So probably you can, I think it should be okay.
Yeah, we would in this case only do the name-based, the thing that helps the name and the separation of the address, we can do it at the border routers once the packet is de-encapsulated.
Yeah, yeah.
Moving on to the next topic, which I worked on, which is the named object multicast. Sorry, something coming on my slide. For named object multicast, what we wanted to see was there is a need for a scalable inter-domain multicast, which is not much used today. Even though what the slide shows is there are a lot of applications that need multicast. For example, there are applications like IoT commands, which you want to send the same command to a bunch of sensors. You can have traffic notification where you're sending the same traffic advisory to a group of vehicles on a highway. You have your classic multiplayer games, Twitter, and so on. And the group sizes vary, how the longevity of the group varies, but in essential all of them need multicast. However, because multicast is not supported that well in interdomain, most of these applications now use unicast because that's the only thing available within the IP framework, right? And the reason interdomain multicast is not used because there's a high overhead, as I'll show next, for maintaining multicast trees. Also, there is no support for mobility. So, for example, if there's a receiver subscribed to a multicast group and it moves, it has to resubscribe to the group, and the entire joining tree and everything has to take place again. So there is no support for dynamic mobility while being part of a multicast group. So what we propose, the named object multicast on NOMA, is based on our named object concept where the multicast tree is actually stored in the global name resolution service. And the way we do it is we assign a GUID to each branching router of the multicast tree, and then we map those GUIDs to the next set of branching routers and their addresses, and so on and so forth until you reach the leaf of the tree. So the way it happens, I'll show it on the next slide, but the tree is right now stored in a distributed way in the GNRS. Intermediate routers don't need to do anything, but packets are encapsulated from one branching router to the next. Where it's de-encapsulated, the GNRS is looked up again and it's forwarded. So it's a name-based tree. Also, it's quite flexible because you can use different types of tree generation algorithms. There are quite a few: shortest path, longest common path, and other things. So you can use any of the different available tree generation algorithms to generate the tree. But once it's generated, it's stored in the GNRS, and then you tunnel from one branching router to the next. So how is it different from IP interdomain multicast? So on the left, what you have is what happens when an IP multicast is set up. A host joins. So for first, the source has to register itself as a multicast source, and that information is flooded to all the other networks. So everyone else knows that there's a source in this domain which is multicast. Now in the other domains, if there's a receiver which wants to receive data from this source, it joins the source, and then that join message is propagated back to the source, and while it's being propagated back, the tree is being generated. The protocol by which the source actually broadcasts is called the Multicast Source Discovery Protocol, MSDP, and there are various ways by which in IP you can set up a tree, but the most common is PIMSM, which is Protocol Independent Multicast Sparse Mode. In comparison, what we do in NOMA is once you join, the mapping between the multicast ID and the receivers are stored in the GNRS. When the source needs to send a message, it asks us, sends a control packet to its first hop router asking it to compute the tree. The router looks up the GNRS, finds the receivers. It already has all the unicast routes, so it computes the tree and stores the tree in the GNRS. Once this is done again, then packets are forwarded. As mentioned earlier, you forward from one branching tunnel from one branching router to the next. So the key point to note is in this case there are no broadcasts required, as well as hosts don't really need to join implicitly. They can be explicitly. They can be joined implicitly. For example, all vehicles entering a highway can be part of a context which can be mapped to a multicast tree by which any traffic accidents messages can be multicast to that group without every vehicle having to explicitly sign up for traffic advisory on that stretch of the highway.
So how did they signal that they want this?
They have to join. They have to agree to an implicit joining a context. But so, for example, I can join a context that I want to receive all notifications when I'm driving related to traffic. Now, they can be, as the vehicle is moving, I can be part of a group which is traffic advisory between exit 5 to 7. And then when I move out of exit 7, I'm no longer part of the group. I don't have to join the next group again. I'm implicitly part of the context.
So what part of that keeps you getting traffic that stops you from getting traffic updates for San Diego?
So there has to be a service manager which needs to manage this context, right? The context manager needs to know that based on this network, based on this location, what are the set of network addresses, and then what are the set of receivers which are part of this network address, and only then the multicast group can be set up.
So you set up once that you join a context that says you want traffic awareness,
Yeah, something of that sort.
and people in California join the same context,
Yeah.
right? But then you somehow you keep updating your location, and it uses that to decide which traffic awareness feeds you get.
You will keep updating your name to network address mapping in the GNRS. But the multicast service manager needs to somehow know what network addresses belong to what location, right? There has to be some mapping between the location and the network addresses. And then based on that, you can know what the multicast service manager would know what set of receivers are part of this location and hence should be part of the multicast group.
So there's only one GNRS for the whole world? There is?
Yes.
That's
It's
the one.
not one, it's distributed.
It's
But yes,
logically
it's one.
centralized.
It's like one of those forests that has many trees, but they're all actually just part of the same tree. Yeah.
Yeah, it's physically distributed across all autonomous systems, but logically the information is centralized.
The routers who join this network participate in a peer-to-peer exchange, which is the GNRS. So logically it is centralized, but it's spread out.
Like I mentioned, in IP multicast, there is some MSDP and PIMSM, and whereas for us we do NOMA, and so we wanted to compare the two in terms of control overhead. This is a simulation where we have a random graph and we assume 50% of the nodes are participating in the multicast group. What the plot shows is as the graph size increases, what's the control overhead of setting up the multicast tree. As you can see, for very small graph sizes, the overhead for NOMA is actually higher, and this is because again the GNRS is physically distributed and there are multiple replicas for each mapping. So this overhead is much higher than simply flooding the source active messages and setting up the multicast tree. But as the graph size grows higher, NOMA actually scales quite well, whereas above 1000 the IP multicast simply becomes not scalable at all.
So one question, Shreyasee, I mean, in the last slide you said like you are inserting a tree, the source router inserts a tree in the GNRS.
Right.
If you have like this ad hoc topology, I mean, then the tree has to be updated, right?
Yes.
So then how does the source router know when to update this tree?
Right. So we, in our implementation, we had some periodic updates. But you're right that there has to be some mechanism of figuring out how frequently or not frequently to update the tree. So if it's a very dynamic group, this update needs to happen quite often. For us, we just kept a constant periodic number. But we also have a solution for mobility, where temporarily we send some repair packets, which is there on the next slide, for a few number of receivers if they are moving around, but not for group. They don't move out of the group, they're still part of the same group.
Oh, so you have some ACK going to the source, but
No,
they don't go right to the sources.
No, the source actually just sends out, the source doesn't do anything. The source sends out the multicast packet. But the first hop router periodically recomputes the tree based on who are the receivers now and updates the tree. Now, how often you do this recomputation is out of scope, but it should be based on how dynamic the group is.
Okay.
But like I mentioned, for mobility, if a receiver is still part of the same group, so it has not moved out of the group, but it has simply changed its location, we leveraged on, again, the mobility first concept of how to address mobility. But in this case, as the receiver moves, what happens is a packet arrives at the old location and it fails to be delivered. In that case, we introduced a temporary repair packet. So the packet is encapsulated with an SID which says this is a multicast repair and is rerouted to the new location, which is shown on the left side of the slide. So on the right, what we did was we did some NS3 simulations for mobility, and we to show how NOMA addresses mobility and what happens in case of IP multicast. So on the right top, what you have is a receiver moving and disconnecting temporarily from the network and then reconnecting. What you see is the blue line is the multicast data that is being delivered, and then it drops to 0 when there's a mobility and disconnection. Whereas as soon as it joins the new network, the repair packets kick in, and then the repair packets is shown in black. The repair packets kicking and they deliver the data. Whereas for PIMSM, you see a dip and all the packets which were being routed to that receiver is being lost until the receiver explicitly joins the group back again. On the bottom, what you have is the aggregate throughput as the mobility rate increases, and as you see, as the receiver becomes more and more mobile, there are more packet losses. So PIMSM plus MSDP has lower throughput, whereas for NOMA the average throughput remains the same because packets are being stored by mobility first. You're doing a GNRS lookup and rerouting it to the correct location. So in summary, we proposed a named object multicast scheme which can support multiple different types of tree computation. There are more details on different algorithms for tree computation in the thesis as well. NOMA implicitly supports mobility. We did simulations to show how it scales well compared to IP multicast. For this work as well, we implemented it on Click, and we did some small feasibility studies on the orbit as well. Moving on to the third part of the thesis, where this is the last work which I've done. I was saying I've been doing, but I've done. It's on low latency cellular core network, and the goal is to look at the requirements for 5G networks and to see how can we support low latency for future 5G using named object concepts. So as you might all know, low latency is a key requirement for 5G. This slide simply shows figures from white papers from all these companies which say what are the requirements for 5G, and they all say we need low latency. However, the exact number varies from company to company. Some might say we need less than 1 millisecond, some might say 5 milliseconds and so on. But still the goal is to reduce the latency of communication using cellular networks. However, if you look at the protocol exchange for LTE, what you see is it's pretty control heavy. On the left side, you have all the control messages that need to be exchanged before a UE can actually send any data into the network or receive any data from the network. You can ignore all the details of the timing diagram, but what it says is that there can be as high as 21 messages that need to be exchanged before any packet can be sent. What this means is more control heavy implicitly means that there is more latency associated with it. Also, another interesting thing to point out is the LTE core network is pretty hierarchical. So there is a mobility management entity, there is a host subscription service, and there are a bunch of gateways, and packets can only go into and out of the network through these gateways. There is this work done by University of Michigan, which is shown on the right side of the slide, which says that where they showed that for within the United States, all the leading network carriers have only 4 to 6 gateways through which any packet goes into and out of the network. This is a source of serious bottleneck. One, it's bottleneck, and two, there is also routing inefficiencies, because now all the data traffic, no matter where you're located, there are only 4 to 6 points within the country where your data can actually enter or exit the network. So how can you achieve low latency in 5G? There are a few ways you can do that. The plot on the top right is also by the same group in University of Michigan, where they ran some experiments to see what is the actual latency incurred by a data packet. So the first packet, because it has to go through all these control messages, actually incurs the most latency, and they even broke it down to different components. So for example, if you improve the PHY and MAC, you can reduce the user plane latency showed in blue. If you improve the authentication mechanisms, you can reduce the authentication round trip showed in yellow. If you somehow improve the control plane and the control protocols, you can reduce the session setup and management latencies. So my work has mostly been focused on reducing the session setup and management latencies, and also the core network latency, which is the one showed in green. But of course, with 5G, you can use newer protocols in the PHY and MAC to improve the latency further. On the bottom right, what you have is the proposed 5G architecture. So compared to 4G, this architecture has been modularized. So they have moved the functions into modules, so it makes it cleaner to upgrade and to change any of the protocols. But as you can still see that they still have the access and mobility management and session management functionalities, which in our view adds a lot of latency and control overhead for data delivery to UEs.
So the first packet has this big delay because it does all its setup as needed?
Right.
And like how many packets do you send in a session that starts with a first packet?
So we also did some I parsed some data sets where I looked at how often does a UE actually need to go through all these messages, and I have that plot in a few later slides, which shows.
Okay.
Yeah, because I used that number for my evaluation to see how often, what's the control overhead and how often does a UE go through this. But it's like, I think hundreds of seconds. I think of the order of that. No, soon enough.
So what causes the re-authentication?
It's
Like
just how the protocol has been designed.
Like it's not, doesn't have anything to do with handoffs or...
This doesn't involve any handoffs, no. That again involves another set of protocols, and that is not included in this. But this is just for a UE to wake up, set up keys, and then set up its mobility management, where it's located, to which base station, and then set up the session panels with the gateways.
But these you're saying are being reset up every, like on the order of 100 milliseconds?
No,
100
millisecond
seconds
seconds.
later.
Yeah. I mean, as long as the UE is active, this doesn't need to be set up. So for example, if you are on your phone doing something constantly, it doesn't need to be set up. But you turn it off, it goes to sleep, and it wakes up, it has to do this again. So what are we proposing? There are two main things that we change from the architecture that exists right now. One thing is we do not use a mobility management entity. We are using the GNRS and mobility first, so it's a distributed mobility management. And the second thing is we remove the gateways. This helps us in two ways. One, it doesn't, we can do away with all the protocols for setting up tunnels to the gateways. And secondly, in the data path now, data can freely go in and out of the network, and there are no bottlenecks in the data path as well. You can also extend this work to use secured UIDs. In that case, we can also, because UIDs are self-certified based on public keys, you can probably reduce the authentication part of the latency as well. However, for the evaluations, I've not considered that yet. What is the protocol that we are proposing? So As you can see, the RRC connection, the MAC layer radio resource connection protocols remain as is. What we are doing is there is no PGW, SGW or MMEs in our system. We still want to have one attached request going into the core network so that the network can verify if this is a valid UE or not. So that's the attached request response in the timeline. On the left between U and eNode B, all the messages remain as is. Now the eNode B talks to the mapping system, which is GNRS in our case, to update the UE location, name to location mapping. Since we removed the gateways, one point to note is the gateways traditionally performed policy and QoS and charging. Now this needs to be distributed across all the UEs. So they would do all the policy management as well as charging anytime a UE sends a packet or it sends a packet to the UE. So given this system, how does the control and the data plane look like? On the left is the control plane. So again, you have the GNRS. The packet forwarding and routing remains the same as described earlier. However, now the eNode B has some policy and charging information which it gets from the HSS. On the data path, similar to Mobility First, you have the identifiers as well as the current network locations for this UE being in there in the packet. And then packets can flow in freely into and out of the network from any of the egress and egress points. So there are no GTPs and tunnel setup and distributed forwarding. We did some simulations. This is the plot I was mentioning earlier. We did some simulations on what's the global overhead for a US scale carrier. There is this paper and this project called Mobile Insight, where they crowdsourced all this data from different carriers to see all these control messages, how often they happen and what. And also, their goal was a bit different. They wanted to optimize. Content placement or something similar to that. But the data set that I obtained from them, I parsed the data set, and as you can see, this one says RRC connection periodicity. This means how often the UE wakes up and exchanges all these messages. So it's about, yeah, this is 100, this is 10, so around every 50 seconds or so on an average, your UE will wake up and exchange all these messages.
So you have like you have seems like there's one collection of CDFs over here and then one,
yeah.
What's the difference?
I'll explain that. The green one is synthetic data, which is for IoTs. There is a projection that a lot of IoT devices in the future will also use the cellular system to communicate. However, there's no data available as to how often an IoT wakes up and connects to the network. So the green plot is based on 3GPP guidelines, where they say how many devices, what percentage of devices will wake up once a day, what percentage of devices will wake up once an hour, and so on. So I use that synthetic data in my simulation, whereas for the smartphones is the crowdsourced data. Yeah, so for my simulation, I focused on one US carrier which reported it had 138 million UEs, and then we looked at Cisco predictions for 2021 and added more number of UEs based on how many UEs will connect in 2021. Based on 3GPP predictions, we added 33 million IoT UEs. For that same US carrier, I also parsed their OpenCell ID, which says how many base stations they have currently. I made some assumptions on the number of PGWs, SGWs and MMEs because that's not publicly available. But the number of PGWs is based on the work done by University of Michigan, which says they have at max 6 PGWs, so that's what I assume. And then for their intra-domain topology, I looked at Qaeda to find their POPs and links so that I can do some data forwarding evaluations. So now given we know how often the UEs wake up, and we know the internal topology, and we know how many base stations it has, what we wanted to look at what is the overhead of maintaining these many connections for these many UEs at different components of the EPC, and what is the overhead for us. So on the left you have what's the overhead for the EPC for 2017, then with the prediction, Cisco prediction 2021, and then 2021 with IoT UEs added, what's the average and what's the max. So as you can see, the maximum overhead for MME can be as high as 5 gigapackets per second to maintain these many number of UEs, which is quite significant. And the reason the MME sees the maximum overhead is because the MME is the mediator of all the control messages between the eNode B and the gateways. Whereas in comparison, what we wanted to compare is what's the overhead for our MME, which is a distributed GNRS, for maintaining the location service. So since we don't have gateways, there is no comparison with the gateways, but for the MME we have GNRS, and in this case a GNRS can store multiple replicas of the same name to address mapping. However, since it's distributed across the entire network, what's the load on each of the routers for maintaining this service? And it's the worst case, it comes to around 800 packets per second. We are assuming all the POPs within that network are participating in the GNRS, so they're sharing the load. For the data plane, what we wanted to do is we wanted to look at what's the routing inefficiency in the current 4G core. We have this use case where there are two subscribers both belonging to the same network and they want to communicate with each other. How does the packet flow? So the plot shows the path length and number of hops that the packet incurs when there are two subscribers within the same network. So as you can see, because all the data gets tunneled through a PGW, what happens is the packets from subscriber 1 goes through a PGW and then comes out and then gets rerouted gets into another tunnel and then gets routed to the subscriber 2. Whereas for our case, it's based on shortest path routing, so the path length is much lower. We also did some prototyping of this. This is based on Mobility First host stack link and open air interface. We had to modify Mobility First code a bit for it to work with the open air interface. We also modified open air interface so that we removed all the gateways. We wrote a custom HSS in our case, which the eNode Bs maintain a long-lived connection to authenticate the UE, and the rest of it is Mobility First based. So you have Mobility First routers and GNRS and so on. And we did some preliminary experiments.
So when you're comparing to this 4G system, right? So are you replacing the MME with something else in your network? So do you have a picture? I missed it perhaps.
Yeah.
Of how the two architectures look.
Yeah, we are replacing MME with the GNRS, which is this yellow cloud, which is distributed name resolution service, and there are no gateways.
But you could have multiple MMEs also, right?
Yeah, you could have multiple MMEs.
So,
but right now the architecture doesn't support it. These are all vendor-specific, custom-made MMEs, and each network only has a few of them. And they are, like I mentioned, there are around 4 to 6 per network. One way to go about it is...
I somehow always thought that each MME was associated with a set of cellular cells or base stations or whatever. Am I right or wrong?
Quite a large number.
How many is it typically?
Tens of thousands.
Oh really, is that high? I somehow thought it was okay. Interesting.
So, but you cannot introduce multiple MMEs without a new protocol, because right now it's all based on going to that central point and all the input-output is from there.
Somehow I thought there were multiple MMEs and they covered, some what they call as radio.
Right.
I forget the name, radio coverage area or whatever they call it.
So, but they kept growing larger and larger with time. So here this is just flat network. Every router supports some functionality, so that there's no need to set up a tunnel and go to a specialized gateway.
So you're replacing essentially all these gateways, the packet gateway, the serving gateway, the MME, in your EPC with this picture.
Yeah, so now
That's
you
sort of
have
what you're saying.
Mobility First routers which do routing and forwarding based on some routing protocol, and then you have the global name resolution service, which is again distributed across all the routers.
So this doesn't change anything in terms of how, for instance, handover happens, or how any of these functionalities in the EPC, right? In terms of how they handle mobility of nodes. How does that change here?
Everything is different.
Right, so you see, look, I'm seeing sort of what you're showing me is like, the overhead there was, maybe I misread this because I was kind of distracted. You said, I think, gigapackets per second versus 800 packets per second.
Right.
Or something like that. Did I miss that, or
No,
is that accurate?
I did
So therefore, what did you give up for that?
Right. So
That's what I'm trying to understand.
Yeah, that's a good question. So one of the things, for example, for mobility, in mobility first, the way it handles mobility is you move an associate to a new base station, you update your information in the GNRS, and packets are delivered hop by hop reliably. So you go up to your old location and then you reroute it to the new location. So that has one trade-off, is that there might be a temporary disconnection, there might be some rearrangement of packets, right? Because you're doing hop by hop delivery as compared to end-to-end reliability. Whereas in the traditional 4G architecture, what you do is a make before break. So there is a very heavy control messages, which I have not discussed in these slides at all. So eNode B instructs a UE that you are now moving to a next.
No, I know that. I'm familiar with that. Yeah.
Yeah, and then you have a bunch of messages with the MME. So that adds into the overhead, but that would ensure there is no break in the connection. So an end-to-end connection won't break in that case. So that's the trade-off.
So there's 12 gigapackets per second, whatever number you showed, right? So this was for what? How many base stations? How many mobiles? What was the total number?
So, yeah, this was based on 138 million UEs plus, if you look at 2021, it's 230. So it's 236 million UEs for 2021 plus 33 million UEs for IoT. And the number of base stations is 637K.
So therefore there is no overhead at all. Why is it 800? I mean, what's the correlation between that many millions of devices and the 800 number you came up with?
So the difference is, these are the messages that need to be exchanged in the 4G architecture versus these messages for our case, right? The main set of overhead that comes in is maintaining the sessions with the gateways. So you have the MME mediating the tunnel setup and the tunnel breakdown between the eNode B and the SGW and PGW. Once you remove that, you remove all these messages in black, in the shaded color, right? All these messages don't need to be there. So that's one case. The other case is with the MME, when you had only 6 MMEs in the network. In comparison, now you're using a GNRS, which is distributed across the network. So when I say 800, I mean it's 800 per router and per POP, which is, there are 82K POPs. It's just that you're distributing the load across the network where everyone shares the load. So per POP, the overhead is much lower.
So in the context of your architecture, what happens if a node is moving? So can your device operate in both the 4G world and your mobility first world? Is there like how do you do what they call essentially like a handover from a legacy system to your system? A big part of the 4G architecture, it is about how do you hand off from a 3G to a 4G system. There's a whole lot of overhead with that too, right?
Right.
So an MME and all these things, how they talk to the old SGSN and all that stuff.
Yeah.
So have you thought about that in your problem?
Not in this context, but there are some, so in the end you need some sort of proxy mechanism to translate from a mobility first world to a 3GPP world or IP world. There's no way around it, right? But we have looked a bit into proxy designs, but not that much. Also for the 3GPP specific, I have not looked into handover between say 3G, 4G or 4G MF. We are assuming that the network is all mobility first based. So we also did these are the last set of slides, we did some experiments on the orbit testbed for what's the latency. for setup of a connection. This plot has no MAC protocol latency, so there's no RRC connection latencies, it's just the latency for the core network protocols. For the distributed core, we have our own implementation, we've updated OAI, and we have our own HSS, which the node Bs talk to, whereas I'm comparing that with the Amarisoft EPC on the Orbit testbed, which is a commercial EPC, but it's still a software implementation of an EPC which is available. And what we find is the average protocol latency for setup for us is around 21 millisecond, whereas for the EPC it's 750 millisecond. And this is again because of all the protocols. I'm assuming the software EPC does, because it's a commercial one. I can't really go into it and check what sort of messages it's exchanging. The next slide also shows another latency experiment, which is now we are looking at the complete latency for setting up a connection for our distributed core versus what you would see commercially. So for the commercial network, this is not an Orbit experiment. This is again from Mobile Insight. I looked at, they had all the control messages there, so I parsed that to find out what's the latency for setting up a connection for a UE, and for the same carrier for which I did the simulations. And again, even though the commercial network has much lower overhead, it's around 181 milliseconds, this is actually much higher than the one which the group at UMesh found, which was around 75 milliseconds. This is a more later, this is a latest work, I think this is from 2016. Yeah, that was from 2013. So the latency has actually become worse. Now it's around 181 milliseconds to set up a connection. Whereas for us, we found it's around 49 to 50 milliseconds. So in summary, we proposed a distributed mobile core network architecture. We did some simulations for a US scale ISP, as well as we did some prototyping and experiments to show some latency improvements in our scenario. Conclusions. The thesis focused on protocol solutions. We proposed 3 main protocols. We proposed edge-aware inter-domain routing, where we have coarse-grained routing information. It enables multi-path routing and forwarding. It also has flexible policy specifications, which is there in the thesis, and it allows opportunistic network formation and mobility. Proposed named object multicast, which enables large-scale multicast. Multicast trees, which are now maintained in the GNRS, and it allows mobility of multicast receivers. We also proposed a low latency mobile core network, which simplifies the core network protocols and enables a distributed mobility management and removes the gateways. So looking ahead, one thing which we observed is that there's a lot of interest on named objects right now in IETF and 3GPP, and both I and Parishad along with Professor Ray have talked to them and attended a few IETF meetings where they are interested in the named object solution. So that could be one route to move forward. Another thing which can be done is to package all of the protocols in a mobile core network and then to introduce it into the system. But again, that requires, as I mentioned, for incremental deployment, some sort of proxy solutions that can allow translation between IP and mobility first packets. That's it. This is the list of publications, and big acknowledgement to all my collaborators. Seem to have worked with quite a few over the years. I hope all of your names are here. And I had to end it like this. I started this a long time ago, and I've come a long way. And the animation should start at any minute now. Yes.
Wow.
So this is to thank all the people, WINLAB, my colleague, my friends, my family who are watching it on YouTube right now, my committee members, thank you so much, my advisor, thanks.
Why aren't all PowerPoint slides in this, in Star Wars? You have things disappear and...
I actually couldn't find a good slide which
So how did you
actually
do this?
did this. So I Google. No, I just there were a few ways to do the animation, but it's still not that accurate. It has to be
It's
much
actually
more
pretty good, right?
horizontal. Thank you.
Yeah, I'm gonna ask you to send me this. It's very nice.
So Narayan, some of this stuff can go into real networks.
No, that's what I was really
It's
asking,
not
that because
really-
otherwise it seemed like just a completely
And
standalone
actually-
activity that's like,
No, she's
what do you do
also
with this?
directly addressing the latency problem, which is going to force a change.
Yeah.
As soon as you have a centralized architecture, both scale and delay. And so flattening it is the key is that every router takes on some responsibility, and then everything is simpler. But yeah, the backward compatible strategy is yet another big
Right,
project.
because it seems like if you really want to make this happen, you have to do that.
Right, so she and Parisha worked a little bit with standards groups, which is hard for, our students
Yeah.
can do a little bit of it.
Right.
So anyway, where she is going to work, hopefully she can have the inter-domain stuff they're doing is based on BGP today, but there could be opportunities.
Seems like there might be a nice thesis on what is called as idle mode mobility, right? I mean, how do you transition from a 4G to your network or from your network to a 4G network?
And
depending
you
on
call
how-
that idle mode?
Yeah, they call it idle, but it's not really idle, right? You're kind of not active. You're not an active call, right? Suppose you're moving, you're connected to some 4G network, and how do you get to?
Notice that she has a prototype which is doing LTE to the handset.
Yeah.
So everything, end to end, it looks like the same service. It has IP coming
Right.
out, but the only thing is in between there's some part of the network.
Yeah, what they call as NAS. I don't know if you're familiar with it. It's non-access stratum, right? The whole business of how do you set up your phone to operate on a 3G network and operate on a 4G network, right? The same phone does it. And they have completely different protocols, and it's a completely non-access stratum.
Right, but this.
So I think this
a
is
little-
kind of like a nice problem where you
this
want to
is
say, how do you
smoother.
do it here?
This is smoother. It can.
Yeah, but I'm just saying like this sort of set of protocol.
Okay, any questions from all of you? Okay, so if not, let's thank Shreyasee, and we have to have a little committee meeting after this. Did you bring any paperwork?
Yes, I did.
Ah, yes. Yes. So did they pass you?
Apparently.
Okay, good.
You were another example of the failure of our qualifiers.
No, I was there. I asked my question and left.
No, we keep having
just
discussions
get a good
about
pen.
why the system is
I-
failing.
You know, here
And
no,
the
it's not
answer is you
that.
presented
This is
like
a failure
full
of
trans-
Zoran, right? Of trying to assign me to qualifying committee. He shouldn't be.
No, I'm not blaming you. I'm not talking about that. I'm talking about the fact that
There's also
Oh, did they pass you?
he's like, you're like a